When a high-speed automotive assembly line abruptly grinds to a halt, the financial clock starts ticking on massive, unexpected costs. For decades, manufacturing has relied on a reactive strategy: run the machinery hard, wait for it to break, and then scramble the floor managers to fix it. The alternative has been preventative maintenance, which relies on arbitrary calendar dates. This often leads to discarding expensive, perfectly functional parts simply because it's the first of the month. Between those replacement costs and the sudden stops in production, unplanned downtime drains over $50 billion from industrial plants every single year. This massive financial loss ultimately stems from a state of operational blindness. To fix it, a factory requires a real-time digital nervous system to move from guessing when a machine might fail to knowing exactly when it will. Dulling that nervous system starts on the factory floor with a dense layer of high-frequency industrial IoT sensors mounted onto critical machinery. These devices continuously monitor the physical realities of the equipment, tracking subtle thermal shifts, acoustic signatures, and the micro-vibrations of heavy components in motion. Instead of periodic manual checks, these sensors pull thousands of individual data points every second to establish a highly detailed baseline digital heartbeat for every machine in the plant. That massive volume of high-frequency telemetry streams out of the physical edge gateway and into cloud processing pipelines, like Google Cloud Dataflow. The cloud pipeline runs signal processing algorithms, transforming messy, raw vibration waves into clean frequency spectrums known as fast Fourier transforms. By separating these frequencies, the system exposes hidden harmonic anomalies weeks before a human operator could detect the problem. The mountain of raw data captured at the edge is only useful because this real-time mathematical translation can expose those invisible physical fault lines. Once those signals are cleaned and structured, they are fed into machine learning platforms like Vertex AI to build specific predictive models. This chart plots the remaining useful life, or RUL. The AI calculates a degradation curve, projecting an exact countdown to the failure threshold. The algorithm synthesizes real-time operational loads and temperature spikes to constantly adjust the trajectory of that curve. This dynamic calculation replaces traditional maintenance schedules, which dictate shutting down a machine next Tuesday simply because a printed manual says so. By anchoring the timeline to localized, real-world machine health, predictive AI turns maintenance into an exact science. This architecture is already preventing disasters in the field, from gearbox decay in offshore wind farms to high-pressure pump seal leaks in chemical processing plants. The ultimate evolution of the system is prescriptive AI. Here, the network moves from simple notification to autonomous action to save the equipment. On the digital side, the system instantly communicates with enterprise ERP software to generate a work order and procure the exact replacement parts. Simultaneously, it triggers a physical response. The AI sends a direct command to the local logic controller, stepping down the failing machine's operating speed to relieve mechanical stress. That dual action response prevents the motor from burning out, keeping the production line running at a safe, reduced capacity until the automated technician arrives. This closed-loop architecture transforms industrial facilities from blind, reactive environments into integrated, autonomous systems that manage their own maintenance cycles.